Thank you very much for this very kind introduction. It's a pleasure to be here, and I'll try to educate you in a field of stellar physics. That's perhaps not what most of you are doing in your daily research. But after last week's experience, we had a whole week of interactions between extragalactic scientists and stellar physicists, and it was very interesting. So I think we can all always learn from each other. So I thought that this audience was perhaps not expert in astroseismology, so let me first try to explain you what it is and why we care about it, how it works in practice, what we do in our daily analysis, treat some various types of stars that may be of interest for broader communities, and let's see where we move on in the future. I tend to call astroseismology, of course I have a biased opinion, the revolution in stellar physics. And you may or may not agree with that by the end of the talk. Oh, that's the wrong aspect. So in general, stellar physics is very well aware of describing how stars live their life. They get born out of interstellar clouds. Some live in clusters, others are more isolated in the galaxy. And we can study this very well in our own galaxy, but also these days in galaxies further away. And we know that stars can have essentially three evolutionary paths. Stars like the sun have a quiet life, as I call it, and they will die as a white dwarf, while stars that get born with a higher mass, they tend to have a much more rapid evolution. They do nuclear burning cycles, making all heavy elements. And so they are the steel factories of the universe, so to speak. And after the supernova explosion, they end up as either neutron stars or black holes. So this picture of stellar evolution is broadly known. And so one could wonder, what is there still to learn in this category? Well, as I say, the devil is in the details. Because if we are honest, then the stellar evolution models that people use today, and anyone, I mean, many astrophysics topics do use the outcome of stellar evolution computations. Internal rotation of stars, there was only one star where we had some information, that's the sun. Until recently, we have made major progress on that. Internal magnetic fields of stars, well, at best we can measure magnetic fields on the stellar surface through spectropolarimetry, but we would like to know how it works inside. And an important aspect really is the mixing inside stars. It is very hard to study because we simply only get information from the outer layers. So the beauty of astroseismology is that this concerns seismic studies of stars very much like seismic studies of our own planet, in fact, in terms of methodology. And that allows you to probe the interiors of stars without being able to do experiments on this interior. This was one of the big frustrations of Eddington, that he could not find a way to probe the interior of a star. It's much more difficult than probing the outer universe. So what is the interesting aspect? If we can detect oscillations of stars, then we can know how the stellar structure is built up and how it behaves physically. And so this is drawn schematically here on this very simple diagram where you have these wave patterns drawn. And the red one is an oscillation that gives rise to a wave that probes the area in this outer layer of this hypothetical star here, and you have another oscillation mode, this purple one, that probes the entire interior of the star, and then you have these green and yellow ones. So oscillations of stars are star quakes, if you like, and they invoke waves, and the travel time of the waves through the interior says something about the physical conditions in these layers, like density, pressure, temperature. And so if I extrapolate that, let's look at this green and yellow wave structure here. You see that the yellow one probes the physical conditions in a slightly different area than the green one. So what do seismologists want to do? We want to measure frequencies of such waves subtract them from each other, and that then allows you to derive the physical conditions of the area inside the star that's green here but not yellow. And if you extrapolate that to many oscillation modes, then you can build up layer by layer the physical conditions inside the star. Okay. Now, of course, we can't look inside the star, so we don't see these wave patterns. What we do is we try to measure the oscillation frequencies by looking at the consequences of these star quakes at the stellar surface. They give tiny little brightness variations. And if we measure them over time, we can deduce the frequencies of the quakes. Yeah? And so that's basically how it works. So I always tend to compare that. I give a lot of outreach talks with music, because it's in fact sound waves. And if I were to, I have an outreach talk next week, and then I bring my flutes and I put myself behind a podium, and I start with a quiz from the audience, because immediately from the sound that you play on a small and a big flute, the audience, even if it's kids, knows very well, first of all, that it's a flute, and secondly, which one is the small and the large one. The frequencies tell you immediately the extent of the musical instrument, so to speak. So stars are just musical instruments for me. As I said, in practice, what we do is a measurement, like you could call it the seismometer. So here is time, and here, in this case, it's tiny little brightness variations that seem to be scatter and noise. But if you put that into a Fourier domain, then you get beautiful oscillation frequencies that pop up. Yeah? That's what we do in practice. So here is reality in a cartoon where 4 stars have been measured by the Kepler satellite. These are real data. And from this, you can see that the amplitude of the oscillations change according to the size of the star, and also the frequency. This goes up and down much faster than this, which is a very slow wave pattern, because the sound waves travel through a big star, right? So by measuring these frequencies, you immediately get a grasp on the size of the star. Yeah? And sizes of stars are connected to ages of stars in a certain way. So this already gives you a feeling that we can somehow deduce stellar ages. And that's, I think, the most important quantity that asteroseismology can deliver to astrophysics. Because stellar ages are even important or interesting for cosmologists. Let's assume we could measure the age of the oldest star in our galaxy. That would be a major interesting measurement. We can't do that yet, but we are trying. But that's the principle. So we can't look inside the stars. These are wave patterns, as I've shown before. Here of gravity mode oscillations. Previously it was from sound waves. But we measure the frequencies, and the frequencies are connected to the internal physics of the star. And for that, we have a mathematical physical model, and we try to connect the measurements to the data in that way. Yeah? Now, what you also know, that's again an experiment I do with the flutes. If you have a rotation inside a star, yeah, if an orchestra plays and you make the podium turn, it's awful. It's terrible because of the shifts of the rotation of the frequencies of the sound waves. Okay, and so when we measure shifts in frequencies of oscillations, we know that they are probably due to rotation. And if we can do that for waves that pass through the stellar interior, we can measure the internal rotation of stars. And that's the second aspect that I think is very important for astrophysics. And so we can compute more or less how this shift occurs. Again, this is a function here that contains the physics of the star. And this is something, the internal rotation rate, that we don't know in general, because at best we can measure the surface of a star, the rotation at the surface of the star, at best. Usually it's even projected, because there is this annoying inclination angle between us and the star. So we are very far from deriving this function here. That's a major goal of asteroseismology. How does it work in practice? This is a quite mathematical field in astrophysics, so that's why I like it. So on the one hand, we have the observational part on the right-hand side. So we do time series observations. We really need a long string of data to measure the oscillations, and we need high precision data, either in brightness variations or velocity variations. That also works. We frequency analyze them, and we get the observed pulsation frequencies. Yeah. And then on the other hand, we have stellar models, and in the very simplistic case that we think we know input physics, then we have a 6-dimensional parameter space, let's say, where the initial chemical composition of the star, X and Z, is unknown to us, the mass and the age of the star. And these alpha parameters, they are parameters connected to convective motions inside the star. So we don't really know well how convection is taking place inside stars, and we sort of do a time-independent convection theory that's described by 2 parameters. Alpha mixing length theory just says how convective bells travel, the distance over which they travel before they lose their identity. And the overshoot parameter is something very important for very massive stars that have a convective core. So their nuclear reactor is continuously mixed. And so when convective bells reach the boundary of the convective area into the radiative zone, they can't abruptly stop, right? They have some inertia, so they overshoot. And if they overshoot, they bring in new fuel in the nuclear reactor. So that's the amount of overshoot we don't know. And so that's, again, a parameter that we want to determine. So assuming that we are perfectly aware of the input physics inside stars, and this is an illusion, this blue box, but anyway, that's what people who use outcome of stellar evolution models assume. We can compute the theoretical pulsation frequencies, and we couple these to the observations. And the aim is, well, either this works well, and then people are happy, because we can get a mass, a chemical composition, and an age with a precision that cannot be reached with any other method so far. I am much more happy if it doesn't work. Yeah? Because if it doesn't work, then that means that this blue box here is not optimal, and that's what I would like to work on. So you have 2 categories for asteroseismology: delivery of high precision masses and ages to the community of astrophysics, let's say, and stellar physics, where we want to improve that blue box. I'm in that second category, but it doesn't matter. Okay. Now, from the point of view of theory, we have 2 extreme descriptions for the oscillation modes. We have what we call pressure and gravity modes. Pressure modes are just connected with sound waves. You all know these very well. And so they are in the regime of the high frequencies. If you mathematically express that, high frequency modes, you can connect the frequency patterns that you measure to the sound speed inside the star. And this is what has been so successful for the sun. On the other hand, so the sound waves have the dominant restoring force is the pressure force in this case. On the other hand, the dominant restoring force can also be buoyancy, and then we have gravity mode oscillations. This is perhaps less familiar to daily life, let's say, but you can compare it with the waves on the ocean. So they have dominantly more horizontal motion. And here you do not expect patterns in frequency space, but in the period space of the oscillations. And now we can measure it these days. So that's basically the theoretical framework that we apply in our daily research. Of course, the showcase of the sun is really our calibrator for the whole methodology. So here you see solar-like oscillations, strength as a function of frequency. Yeah? And so all these lines here are the beautiful solar oscillation frequencies, sound waves. These are pressure modes in the case of the sun. And you do not need to be an expert in time series analysis to see that this is not a random scatter here. There are clear patterns, right? So this is the large frequency separation, which is connected to the interior sound speed inside the sun, okay? And so if I were to blow up this, then you could see some refined structure. Huh? The lines are a bit thicker here and here and here and so on. Yeah? So this whole structure, if you analyze it in detail, you can measure the shifts in the basic sound frequencies due to rotation, as I said before. And that requires very refined measurements. If you do that, sorry?
Is this a power spectrum of the total brightness of the sun, or is this spatially resolved?
No, this is the sun as a star.
So
yeah?
integrating all the light.
But for the sun, we can do both, of course. That's the only star where we can do it both. I'm just comparing this to stars to come where we only have the integrated light. Yeah? So if we invert these frequencies, remember that there was this formula here, this one. Yeah? We invert this integral equation, we measure this, we identify these wave numbers, we know more or less the basic model of the sun, and then we can say something about the interior solar rotation. Okay? And that is what you see in this color plot here. Yeah? So the sun is not a rigid rotator, and as you can see, in the outer convective layer, which is indicated here, there's differential rotation. But as you go in the radiative zone, here this dashed line is the transition from a convective zone to the radiative zone inside the sun, then it becomes almost rigid. And this was sort of going against the idea that there was a dynamo in the interior of the sun that creates the magnetism, because it's the opposite, okay? So here you see that plotted. So differential rotation in the outer layers of the sun, that's what we had been measuring up to 30 years ago. You have a question?
I'm just wondering if there is a unique solution, or you have some complicated likelihood?
For the sun, we have a fairly unique solution to the rotation profile, I should say, because we have hundreds and hundreds and hundreds of acoustic modes detected in frequency. And the precision is, we have more than 20 years of data, right? So, and we have a very good solar basic model that was already close to reality. Yeah? So this inversion and derivation of the rotation works very well if you have a blue box, let's say. That's not too bad, but you have to be close to your solution. Okay, so that's one of the things where we are not as far yet for stars and for the sun on some aspects, but I'll come to that. Yes, I know. That's a very high simplification. Yeah? I'll also come back to that. Because indeed the sun is just one simple star. And now we want to do that for all sorts of stars. Yeah? That would be great. So here is the famous Hertzsprung-Russell diagram, but this time from seismologists. Yeah? That means that all these areas that you see indicated here, these are all classes of pulsating stars. So you have the evolution indicated there with some tracks, full black lines. And all the ellipses there indicate stars where we know if a star passes there throughout its life, it starts having oscillations for whatever reasons. Yeah? And you see that we can do, in principle, seismology throughout the lives of the stars in very many different phases. So one of the key issues for nucleosynthesis computations, for instance, in our galaxy and other galaxies, is about massive stars. These are really the nuclear reactors of the universe. And so what we would like to know is this overshoot parameter for them, because that determines how much fuel is in the nuclear reactor and how long they live. And up until, let's say, a few years ago, we were just assuming that we had an overshoot value of a specific size. Yeah? Now we can tune it seismically. So that's one of the aims. If you cover this HR diagram and see all these stars, then we have oscillation periods that range from a few seconds up to years. So this tells you that there is an immense variety. And that's, of course, connected to the huge difference in size and density of stars. Okay? How does it work in practice? Well, we have received an immense boost. It's really a nice period to be an astroseismologist in these years. because we have two space missions that were originally designed and sold and are also doing exoplanet hunting. So what do you need? You need ultra-high precision when a planet passes in front of the star, that you can see transits, parts per million precision. But that's exactly what I, as a seismologist, also need to find the star quakes. So we have this very nice collaboration in the exoplanet and stellar physics community, because we both need the same data, and they can have their planets and I can have the quakes. That's the way it works in practice, okay? So uninterrupted data, this is a pulsating massive star measured by Corot. This is a pulsating intermediate mass star measured by Kepler. And you have to imagine that some stars do have periodicities of their oscillations, typically 1 day. So I did these type of studies since very long from Earth observatories, walking to my telescope every night, and I introduce a periodicity of a day into the measurements, because that happens to be the periodicity of our planet where we live on. And then you have to cut in these light curves daily, and then it's as if the star doesn't pulsate, because after a day it's sort of back at its oscillation phase. So this is really a big step ahead, the space missions having uninterrupted data for longer term periodicities. Yeah? So how does that work in practice? Here I show two stars. I like these two stars because they are almost copies of the sun, and they are together in a binary system. And you see here the beautiful comb structure. So frequency, this is power in terms of intensity here. And again, you see this very clear structure in the frequencies. The large frequency separation, so characteristic of oscillation waves that are sound waves. Yeah? So what do we do as seismologists? We have this frequency separation. We cut, paste, and put the frequencies on top of each other in what we call an echelle diagram. So here you see frequency modulo the large frequency separation. Yeah? And these frequencies, you know, the sun peaked at 3 millihertz. I forgot to mention that. And here you see this star peaks at, well, between 2 and 2.5 millihertz, and this one a bit further. So these are copies of the sun from their outside, but the oscillations already tell you that they are a bit larger. A bit lower frequency, think of the flutes, so the violin. So that means a bigger musical instrument, okay? And so then, from these structures, we can do this modeling according to the scheme that I have explained. And that gives you then a very tight constraint on mass, radius, and age. Now, for these two stars, these are among the brightest stars observed with the Kepler satellite. This is way beyond the capability originally designed by the engineers, because this is so bright objects that you have a saturation of your CCDs, but that works magnificently. So that was a very nice progress that we could make. And in this case, if you look at these measurements here, the red are the theoretical predictions, and the black symbols are the measurements. And for most of them, you don't even see the errors because it's so precise. But if you subtract this from each other, then you see some kind of deviation, and that's what plotted here. So deviation as a function of frequency for different types of modes. So the colors mean different types of modes according to the quake structure, let's say. Yeah.
Can you help me by telling me in the middle row the vertical axis?
The vertical axis is frequency in millihertz. Sorry about that. And this is frequency modulo the big frequency spacing. So the spacing that you can measure between these. We call that an echelle diagram. Yeah? It gives you the structure of your oscillations. Yeah?
Can you actually calculate the power or just the frequencies? Because I can imagine that the star can excite different modes. So
Yes, these are all different modes. So we,
for example, I can imagine two identical suns with the same frequencies, but one excites one mode and the other one excites other modes.
yes.
Just the change of the spectrum doesn't tell you that the stars are different.
No, but then we have to zoom in a refined way into these frequency peaks, because they have a certain width. And if there is another type of mode excited, then that must mean that there is another that there is a detail in the physics that is different.
But can you actually calculate the power spectrum or just the frequencies?
We calculate the frequencies in the assumptions that we have an eigensolution to a mathematical problem. So we cannot really explain small deviations from the peaks that you expect. Right? We can also not compute the height of these peaks because that's determined by the very non-adiabatic outer layers of the star, where you have energy loss, and we do not master the way to compute that. Yeah.
This is my point. Just looking at these two figures, we don't know that the stars are different. It's only if we cannot observe it that the difference in frequencies are different between the two stars.
Yes.
That the height move doesn't tell us anything.
No, so I can say how big the star is, what its mean density is, but I cannot do a refined interpretation of its physical processes in the interior without exploiting that. That's what you would need for my blue box, right? Yeah. Okay, so I was explaining about these deviations that you see here, and these are periodic deviations that you expect from the pattern, and that's connected with the fact for these stars that we have helium settling in the outer convection zone. We know that also for the sun. So from fitting these deviations and playing with the helium content, we can derive in a non-spectroscopic way how much helium is in that convective zone. This is also a new aspect of stars that we don't have because these stars are cool and they don't have helium lines in their spectrum. Okay. Let's move to other stars now. The sun will evolve to a red giant when it has exhausted its central hydrogen and will do hydrogen shell burning, and after that helium core burning. Yeah? Some stars start helium core burning explosively after what we call a helium flash because the matter is already too degenerate when you reach the temperature for the triple alpha reaction. Some stars avoid that because they are not degenerate in their helium core. From the outside, we cannot tell the difference because these are just big red giant stars. It's purely an inside process that makes the difference between these two evolutionary states. And so one of the big discoveries that we were able to do from Kepler, you can see here, this is again an Echelle diagram. So frequency as a function of frequency versus mean spacing. Yeah? And here you see a ridge of modes. Here you see another one. If I go back to the previous plot, so you see here 4 ridges. Yeah? And so that's what we had expected also for these stars. There's a ridge here, there's a ridge here, and this is a whole mess. Yeah? And that's fantastic. As I said, I am one of these people who prefers to be in trouble, because then you learn something. And this was a major discovery made by my student, Paul Beck. And I'm showing here mixed modes. This is an animation of stars that have mixed modes, and these modes, they have acoustic character in the outer envelope, and in the interior they have a gravity mode character. Yeah? So these are the two restoring forces that play together. And in that sense, you can probe much better the interior of the star because gravity modes are the ones that probe the internal regions. We don't have such modes in the sun, so this is physics we can't do for the sun, but we can do it for successors of the sun. And so we have thousands of red giant pulsations now where we can then have the two diagnostics. So sound waves gives you frequency separations, and these couple to the internal sound speed. Gravity mode oscillations give you period spacings, and these couple to the interior buoyancy frequency, as we call it. And that is connected with aging, because if you can probe core regions, then you have a better handle on the age. So here you see all Kepler stars, the frequency spacing on the x-axis and the period spacing on the y-axis. So by measuring these two numbers in frequency analysis for all these stars, you can see that these are the stars that are in the red giant branch. These are doing hydrogen cell burning, Well, these stars here are doing helium core burning. And so we can see what type of nuclear reactor they have independently of their similar surface. Yeah? And the red dots here are stars that are burning helium, but that have avoided a helium flash because their cores are not degenerate. So this is a major asset now, and this helps galactic people with their studies, because by measuring two numbers from oscillation spectra, we can tune the ages of stars. I'll come back to that later on. Another major discovery is, again, the rotation, because these same mixed modes, after more than 2 years of monitoring with Kepler, that's the time we need to resolve the rotational splitting, we were able to deduce that the rotational splitting in these mixed modes, so here you have radial modes, L equal 2 modes, these are these mixed modes that have this messy pattern in the Echelle diagram, and these do feel the rotation of the star in a different way. Because some of these modes, here I've plotted these kernels that are in that expression, these ones have pressure dominated, let's say. That means that the dominant restoring force there is pressure force, but they are also affected a bit by buoyancy. And here it's the other way around. And so these functions are different, and if you plug them into that equation, then it means that you can use the gravity-dominated mixed modes to get information on the core rotation. While if you use the pressure-dominated mixed mode, you can get information on the envelope rotation. And then you can see if it's the same or not. We cannot do this for the sun. So that's a bit weird. We're in the situation that we can do this now for several thousand red giants in our galaxy, but we can't do it for our own sun.
What are the masses of the giants that you're building?
The masses of the giants are, well, if I go back, we go from more or less 0.7 to 2.5, intermediate masses, I would call it. Okay.
Is the range of frequencies that you showed for the red giant, is that the entire range over which the pulsations are measured, or does it extend beyond that? On the next
slide?
The one that you just showed of the red giant.
Yeah. No, this is just a very small zoom to show. So in practice, we go from, let's say, 40 to 300 microhertz, more or less, for red giant stars. Yeah. And so here is this. I like this plot. I made it recently. Here is the gravity of stars. That's sort of saying how old they are. It's connected to their evolution. And on the y-axis is the rotation frequency of stars. As I said, it's very difficult to measure this because in general, spectroscopists just measure V sin I, the rotational frequency projected over the line of sight and at the surface, right? Here you see a diagram where we can now, through seismology, do the core rotation rates. Yeah? And these are all these blue dots. These are all red giants for which the core rotation has been measured from mixed modes and seismology. For some stars, a detailed inversion was possible, and so you see the core rotation connected to the surface rotation frequency by this dotted line. Our sun is here. I cannot plot a blue dot for the sun. We don't know how the solar rotation is in its interior. We just don't know. Yeah? And a major question mark there for the exoplanet fans among you, this angular momentum diagram is very empty for the moment, and we would like to fill it in this area when stars are younger, because angular momentum loss or transport or distribution in host stars of planets is connected to the total angular momentum of systems. So that's something to keep in mind. Now, let's move on to higher masses. Yeah? Here are Kepler data. All periodograms I'm showing are from Kepler of A and F type, so intermediate mass stars. Yeah? And you see we go all the way from near 0 microhertz, very low frequency, up to 250 microhertz. So that's an immense range here. And this is an example of a very nice star that has both high frequency oscillations, strongly peaked here, and low frequency. So these are stars that are now very different from solar-like stars in the sense that there are no acoustic modes due to outer convection, but these have self-driven modes that have a very different pattern here. And this seems like a very sparse frequency spectrum, but if you zoom in and do a detailed analysis, then you see hundreds of frequencies. And so from this, again, this is what we call hybrid pulsators, gravity modes and acoustic modes. And we can deduce the average rotation of this star. It's 65 days in this case, and envelope to core rotation, again, for these type of stars. So this is another one like that. So if you find one that does something weird, then so the question is it an exception? It's not the case. There are intermediate mass stars whose rotation in the core and in the envelope are almost the same, and that should not really be, because during evolution these stars grow a little bit, and conservation of angular momentum would imply that their core would tend to rotate a bit faster and their envelope a bit slower. That's not what we measure. So interior rotation of stars has surprises for us. And moreover, there are several stars that have ultra slow rotations. Something must have broken them down, because we believe that when stars are formed, when they are accreting, they are spinning up. So we have to revisit our knowledge of stellar evolution in this aspect. So what can be an explanation? Well, I'm claiming that internal gravity waves is something we should take into account, because so far this has not been included in this blue box that I showed in terms of input physics. How does that work? Well, stars that have a convective inner core, these convective motions, they trigger gravity waves, and these can then pass their angular momentum inside the star. And this has been computed. Look at the movie here. Rotational frequency as a function of interior mass of the star, and you can see that the rotation rate can change drastically as the star moves into its age pattern. Here you see an age. This is for a solar type star. That's just to say that if you look at these type of theoretical predictions, the rotation frequencies in the core versus envelope can take many different values if you consider this physical phenomenon. This sorry? Yes, but for a one solar mass star only. And these are very old, well, 10 years old. And so now we are redoing these things. We are trying to do that to see if this can be an explanation of why some massive stars behave as we didn't expect them to behave in terms of their rotation. And so Tammy Rogers is sort of leading that research here in the US by doing also 3D numerical simulations, and then we hope to export that to a 1D description that we can then plug in to our stellar evolution models. So it's not yet realistic to do 3D stellar evolution for the time being. Now let's even go to higher masses. The first time we saw period spacings in massive stars was only 5 years ago. This we did from the Coral Space mission. So what you see here is the period spacing as a function of period now, because we're in a different mode regime. And here you see the measurements of one star where we had 8 period spacings detected in a corolite curve of 5 months. And that gives us a handle on aging of massive stars, which is of importance for chemical evolution computations. Yeah. This is the Kepler analogy that in fact came up last week when we were at the conference. And this is another B star where you can see here all the periods plotted. So these, you see these dotted lines, they give the real period spacing, and that is really connected to 2 things: the internal rotation of the star and the mixing properties inside the star. And so here you see a pattern, the observed pattern of all the period spacings, and it's going down, right? For this star it was not going down. Why is that? Well, this star is an ultra slow rotator, almost standing still. It's layers. This one is a moderate rotator. And so then these period spacings get tilted. That's again the computation of this rotational effect. And this is a first model that we certainly have to refine, but that more or less gives you an explanation of what is going on in this star. So these are measurements that could only be done after 4 years of Kepler monitoring. Yeah? And so here we take full advantage of the very stable light curves that we got from that nominal mission. So if you look at that star, you see the period spacings. You don't only see that in this case, but here you see rotational splitting. You see, this is a triplet, nice triplet. Here, triplet, triplet, triplet. So if you analyze that in detail, then you get a handle on the interior rotation with a much higher precision, because you don't only see the pattern of the period spacings, you also see the exact splittings. So here is another star that is ultra slow in its rotation. It's a B star, so it should be a rapid rotator. It's not. And we can model the period spacing and find out an inverted rotation profile. This is the first one we ever obtained of a massive star. And it's not a nice, cleaned, colored diagram as for the sun, but it's for a massive star. And what you see, and we cannot avoid this, is counter-rotation in the envelope of this star. This is not at all what theory says that we should have found. Not at all. And so this is something where the community is still trying to digest. I should admit that not everybody is happy with this. Stellar evolution people are not happy with this. But that's what the star is doing.
What is the mass?
The mass of this star is 3.5 solar masses, more or less.
It's on the main sequence.
It's on the main sequence, very young. Yeah. So it should have rapid rotation if our star formation theory is correct, and it should not be counter-rotating in its interior. Yeah. On the other hand, geophysicists, they don't see any problem at all with this, because gravito-inertial waves in the Earth, that's common, right? So we will be following up on this, and we are trying to hunt for more stars now to see if this is common or not. Okay. It requires 4 years of data, and you have to imagine that the Kepler satellites was, of course, built for exoplanets. 150 stars measured 4 years long. Nobody wanted bloody B stars because they are a nuisance. It's really annoying if you want to find planets to have such high mass, bright, shining stars. There are no planets there. So this was avoided to the best of the abilities. Yeah? So how do we find these stars? From artificial intelligence codes that we let loose on this massive data set. And that then tells us, oh, there are patterns in the light curves that resemble the ones of B stars that we have studied from the ground. And so in this way, we did guest observer proposals for Kepler, and we have about 10 B stars, 10 out of 150,000. And this one was number 1, and we're now doing number 2 and number 3, because it's really manual analysis with a lot of work power involved. Yeah? But that's the way how we could make profit of the Kepler mission, even though these targets were not at all foreseen. Yeah?
So omega of R is the radial coordinate. So at every
Yes.
so at the same radial coordinate, there is the same omega.
Well, we cannot. We only have, if I put back up this slide, we only have 19 triplets detected in this star. So instead of hundreds and hundreds for the sun, we have to invert, yeah, the rotation profile from 19 data points.
Yes, but what of the radial coordinate and not of the cylindrical radial coordinate, if it's a rigid rotator?
Well, we resolve this by choosing a resolution in the rotation profile. I'm not sure I'm understanding your question.
Is omega equal on radial shells? On shells, or is
Yes,
omega equal on
here.
cylindrical shells?
Well, we can't make the difference, frankly. This is a very first estimate. So we made this profile for, let's say, 2 shells, and then for 3, and then for 4, and we can do that for up to about 10. And in every case, the conclusion is the same. There's counter-rotation.
Yes, but I would guess, for example, if it's a radial rotator, they will choose any shell, it will go from 0 to the maximum density. I mean, at the same shell. So, what does it even mean? If, for example, the model you chose is completely applicable for the star when you see it.
Yes.
So this is like a hint. That
Yes.
It's not a radial rotator.
Exactly. A hint is a good word. And I cannot provide a smooth profile because I have too few data points in this
What are
case.
these red boxes? Are these 3 sigma error bars?
Yeah. Well, yes. So they are large, admittedly, but the point is that we cross a line here. And there are inversion issues here, certainly mathematical issues, but we can't avoid crossing that line. That's the point. Yeah.
So the core is almost not rotating at all.
Well, we can't. The core is indicated by this green dashed line, right? And exactly, it's standing still, more or less. Not what we had expected. Here's another case that came up last week. This is an F-type star. It's not a B star, so this is typically near 2 solar masses, where we see period spacing going down, and for the same star, so period spacing going up. These are retrograde modes. These are the ones that have a wave pattern opposite to rotation. These are prograde modes. These are waves that go along with rotation. And so these two go together in this diagram, and from this we will be able to deduce some information on the rotation frequency again. And this is explained here in this theoretical study that was done some time ago without any application, where you see dipole modes. And so this is for a non-rotating star. This rotates 20% critical, 40% critical, and that's how you expect to see the periods change in the period spacing diagram. And this is when you add mixing, additional chemical mixing that's not included in our blue box for the moment, because we don't know how to do it. But then you see that this gets smoothed out. So from this measurement, without having done modeling, because this is a very fresh result, I can already predict that we will need additional chemical mixing inside the model, because this is too smooth. If you look at these period spacings quite often, then you know that you have to take that into account. Let me move on. This covers the whole range in masses where we can do seismology these days. These two are Corot stars and the others are Kepler stars. This star has 24 solar masses. That's an O-type star among the more massive stars in the universe. And so it's big, young. And we move all the way up to the power spectrum to 2 solar masses there, which I still call it intermediate mass. And this is a measurement of this overshoot parameter. Remember, I told you that for a convective core, you really want to know the mass in the nuclear reactor. Current standard models, let's say, would put it at 0, so no extra fuel during the core hydrogen burning. And these are the measurements connected according to the error bars. Admittedly, they are still large for some stars, but for the 13 stars where we have done this seismic measurement now, we come to the conclusion that there is more mass in the core than what standard models have. And to give you an idea, the dashed connected circles there are eclipsing binaries. So from eclipsing binaries and isochrone fitting, you can also get the overshoot parameter. That's a totally independent, different way, and these two types of works point to the same direction. And so massive stars live a bit longer in general than anticipated, well, up to 20% long. So that's something to take into account in nuclear fusion, nuclear synthesis models, let's say. Okay.
Are these done for the same stars that are eclipsing binaries and
No, we're trying real hard.
that would be great.
Working on it. Yeah, we're doing that. And we have a few Kepler stars. But the point is why we are so slow. We need to monitor the orbit spectroscopically. And then and this is ongoing, coming. So, astroseismology can feed into galactic archaeology. Here is a plot of what the CoRo and Kepler space mission delivered in terms of red giants. So the CoRo mission was pointing at different fields, but only for 5 months, which is short for this type of work. This is the Kepler point of view. And then you can use these scaling relations that are connected with the sun and the frequency spacings. Yeah? So these scaling relations are here. You measure the spacing, as I've shown, and you measure the position of the maximum. Not the height itself, because as I said, we can't really exploit that. But the position of the maximum power and the spacing is connected to the mass and the radius of the star and its effective temperature. Temperatures are fairly easy to measure from spectroscopy. So this is what we are doing. We measure that from spectroscopic analysis, and then this measurement and this measurement, 2 numbers, deliver you masses and radii, and we are typically at 2% precision in the radii, 5% in the masses, and 10% in the ages. So that's what we can deliver now, and that's what the conference last week was all about in Santa Barbara, so that we can give this to galactic studies, and that's a big asset. Okay, you can deduce from that, if we provide a mass, a radius, and we have a spectroscopic effective temperature, then you have the luminosity, right? Then you have the distance. So we are at a point that we give 10% seismic distance estimate. And we cannot wait to get Gaia, because that will be a totally independent measure, and then we can calibrate. Exoplanets, that's a hot topic, and so we go hand in hand, so to speak. This is a CoRo star where we have oscillations just like for the sun of an exoplanet host star, and from deducing this beautiful power spectrum and frequency separation, we do aging of the star. And then we have the age of the planetary system, of course. So that's a big asset as well. So here we are feeding into the exoplanet community. And for the Kepler mission, you see here about 500 dwarf stars, not too different from the sun, where seismic ages have been determined. Now we move to K2 to come to the end. K2 is wonderful in one aspect and is a downgrade in another aspect. It's a refurbished Kepler mission. It can do very many different positions along the ecliptic. That's fantastic because we can point at clusters, we can point, and well, not anywhere you want, but still. But we can only measure the stars for 3 months. And as I have shown, the rotational results from seismology require longer. So K2 will not be able to deliver us internal rotations of stars in general, but it can give us ages, masses, and radii of very different stars, including metal-poor stars that we have not been able to measure for the moment. Yeah? So this is ongoing, and we keep writing Kepler K2 proposals as we speak. Premain sequence stars have also found their way into astroseismology. This is from a very recent paper in Science, where the frequencies of stars as they contract to the main sequence, to their birth, has been coupled to a seismic quantity that we have measured. And from this you can do also aging, and that is of course then very interesting if you could do that for stars where planets are forming. So that is also something we want to exploit with the K2 mission. Unfortunately, there are not so many places where the satellite can point where we have known Premain sequence stars, but we have several of the proposals. So as I said, we are waiting for Gaia, because then Gaia delivers us a radius or a distance essentially, but with an effective temperature that translates into a radius, and we lose 1 dimension in our space of variables, let's say, and then we will get a handle on the input physics much better. We can do the same if we have a good interferometric radius. And so this is another aspect that we are trying to work on, but it's very difficult and technical to get a radius up to a high enough precision to help us, but it's in principle possible. And then very far away, in Europe, we are working on the Plato project. It has just been selected. Plato is a mission to stare at two fields during a long time. Here are the two preliminary fields. We will tune that. This is the Kepler field, just to give you an idea, and these are the coral fields. So Plato will stare for 2 years in one direction, for 3 years in another direction, and then it has step and stare phases. And the aim is really to go to hunt for exoplanets of low mass in long orbits, so to have copies of the Earth. Just like Kepler, we will find an immense amount of astrophysical information that is not the main aim of the mission, but it's part of the complementary science, and you are very welcome to register. It's free. It's European paid mission, but the complementary science that I'm leading is not connected to dollars or euros. Okay. So to come back to my statement, is asteroseismology the revolution in stellar physics? Well, we moved from parts per thousand to parts per million precision just by space missions. We had a few bright solar-like stars. Now we have thousands of stars across the HR diagram, and we can do physics of stellar cores now, even though we still have to refine it. So I think we have come a long way. It is true that this is a topic that is perhaps European-led, if I may say so, and I'm very happy that since 2 or 3 years I'm receiving American PhD and undergraduate students even, because we have a very specific semester-like program at our university dedicated to this. And so again, last week I got the questions, can't you receive students? I'm Belgian, right? And so there are specific funds like the Belgian American Educational Fund. So if you have students or if you want to get educated yourself, you are very welcome in Leuven University. Thank you.